Hello, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon.
Waalaikumsalam warahmatullahi wabarakatuh. Good afternoon, Prof.
Everybody
Prof.
listening?
Good afternoon, Prof.
Bismillahirrahmanirrahim. So, we begin with chapter 5. So, in chapter 5, today I will discuss on 5A and 5B on the case study, okay, where we apply all the theories that we learn for system ID procedure, beginning from experimental setup, data collection, pre-processing data, model structure, parameter estimations, and model validations, and then some discussion, okay, throughout the case study. So we will, today we will focus on hot dryer data, okay, hot dryer data from a laboratory, and this data was used in the system ID toolbox by Leonard Jung and MATLAB. So we begin with 5A. So 5A is on a hot air blower system using a programming approach, while chapter 5B is programming on a hot air blower system using a GUI or GUI, as known as a graphic user interface. So, so this is the schematic diagram for the hot air blower systems, okay? And the picture here is showing you the real trainer that available in the laboratory, okay? So we are going to estimating simple models from a real laboratory process data. So the content of the presentation is we will describe on the system description, setting up data for analysis, pre-processing data, estimating non-parametric and parametric models, analyzing the estimated model, estimating models with prescribed structure, validating the estimated model to experimental output, and comparing estimated models and some additional informations. So in order to do that, we need a MATLAB software, okay, and this MATLAB software must have a system identification toolbox, okay, so I hope everybody have this toolbox installed in your desktop, okay, because you are going to do this toolbox during your assignment. And this toolbox is will be used to develop and to analyze the simple models from a real laboratory process data. So we start with the small descriptions of the process, learn how to import the data from the toolbox and pre-processes conditions, and then we proceed systematically to estimate the parametric and the non-parametric models. So once the model has been identified, we compare the estimated models and the validate models to the actual output data from the experiment to see whether the proposed estimated model follow the real models that we captured. So the data name is hair dryer, is taken from the feedback process trainer as mentioned in Leonard Jung books, okay, publication 1999, page 525. So the process of this hair dryer, it starts as follow. So the air is fanned throughout the tube and will be heated at the inlet, okay, and then the temperature is measured by a thermocouple, thermistor. So we are using thermistor because thermistor is the sensor that can detect small changes of variation in temperature compared to thermocouple. Okay, so the input data is named as U, okay, which is the power of the heating device. So power, the unit is watt, okay, and it's just a mesh of resistor wire that being heated, okay. So heated, so the air will flow to the mesh of resistors wire, and the flow, the movement of the air is pushed by the fan, okay, near the heater wire. And then the output is the temperature, okay, from the tube output, okay. Okay, so this temperature will be detected by thermistor, and thermistor with the associate signal conditioning will convert the physical signal, which is the air temperature, to voltage. So it converts from degree Celsius to voltage value, the equivalent voltage value. So this is the trainer, the data where we capture the data from. You can see that here is the motor and the mesh wire, okay. So the motor will rotate the fan, and the air will moving from the left to the right and go through the mesh wire, which is heated, okay. Then the flow will go throughout the pipe, okay, and go to the exhaust here, exit, okay. But before the air go to the exit, so it will be detected by this thermistor, the black color. This is the thermistor, okay. So the thermistor will detect the temperature, okay, the heat in degree Celsius, and then convert to the voltage value, okay, and then go to the summing junction. So the display will be shown here, okay, in the meter, the temperature value, okay. So this thermistor will be associated with the bridge circuit, which is the signal conditioning circuit. And for this trainer, as I told you in chapter 2D, if open loop, so it is a first order system, okay. But if it's a closed loop, okay, so it is a second order system, okay. Two poles lah. First order is single pole, second order is two poles. So this trainer also is come with two type of controller. One is the continuous controller, and the second one is the two-step controller. So the continuous controller is the PID controller, proportional, integrate, and derivative controller. And the two-step controller is on-off controller, okay? On-off controller. So on-off, some books call it as a bang-bang controller. Some book calls it on-off controller. Some books say two-step controller. So both are the same, okay? Both are the same. So it will go to the correcting element, which is the summing junction, and then it will compare the set point of the temperature and the output, the real output of the temperature. So this is the real system in the picture, which is obtained in the laboratory. Okay. Okay. So there are many style of prototype. So first we have to load the data. So the data is already in the MATLAB. It's associated with the MATLAB workspace. So we just call, just type load dryer data, dryer 2. So it will go to the database of the dryer 2, and then it will upload the output data, which is 1000 output data, which is labeled as Y2, okay, which is the measurements of the temperature in the outlet air stream, and then the input U2, okay, also will be upload, okay, which is 1000 input data points consisting of the voltage applied to the heater. So the input was generated using a pseudo-random binary sequence, which is switches from one level to another with probability of 0.2. So the sampling interval used to capture the data, okay, 1000 data is 0.08 seconds, okay, 0.08 seconds. So we are captured 1000 data. The length of data is 1000. The sampling time is 0.08 second or 80 millisecond. So what is the period of the experiment? What is the period of the experiment? Anybody knows? Alkali? Hello, Alkali? Saravanan? Hello, Saravanan?
Sir,
What is the period of the experiment? Tempo masa eksperimen to capture the data. The length of data is 1000, the intervals is 0.08.
80.
80 seconds. Yeah,
Yeah.
correct. It's 80 seconds, which is 1000 multiplied by 0.08. So it is 1 minute, 1 minute 20
seconds.
seconds. Okay. So the experiment period, when we start capture the data, then we stop capture the data. So it's 1 minute 20 seconds. Everybody okay?
Yeah.
All right. So the next step is to set up the data as a ID data object, which is dry. The command is dry. Okay, dry ID data Y2 U2 0.08. 0.08 is the sampling time or the intervals between one data to another. U2 is the input data, Y2 is the output data. Then we want to get some information about the data. So how to do that is just type the name of the ID data object at the MATLAB command window, which is dry. Okay, so it will give you the data, which is the time domain. Okay, with 1000 samples, intervals 0.08. The output is Y, the input is U. Then we use the command, which is the get dry data. So it will give you the time domain data, the output data, the name, then the unit, and the input data. Same as name, the unit, and the intervals, which is 0.08, and the names of the experiments and so on. This is just coding for a record of coding. So for better bookkeeping, usually we put the names of the input and output data. So the input data will be power, the output data will be temperature. Okay, and the time unit is second, and the input is watt, because power, and the output is degree Celsius. Then we have the data ready, so we choose the first 300 data points for the models. Okay, for example, ZE is equal to dry 1 to 300. So we have 1000 data, so we want to plot the first 300. So the way we use the command is ZE, okay, is equal to dry 1 double colon 300. Okay, so we get the 300 samples data. So we plot the data. So this is the data that we obtain. Okay, so this is the input. Sorry, this is the input, the pseudo-random binary sequence, and this is the output. Okay, for 300 data. All right. So you can see that the output here. Okay, try to follow the input below, right? According to the random binary sequence, right? Okay. Then from the plot, we can see that the data have a DC offset. Why? Because it didn't start from zero. Okay, must start from zero. So you can see that the data is not start from zero. This one also not start from zero. So we have to do some pre-processing data, which is known as Detrend. Okay, so Detrend is the command that we use. Okay, in the MATLAB. Okay, so that we can remove the constant levels and make the data at zero mean, meaning that it start from zero. So then we plot. So after we plot, you can see that the data is start from zero here. Okay, so it start from zero. Same as well, this one start from zero and start from zero. So now we can analyze the data. So this process, we call it as a pre-processing data. Okay, so we clean up the data. Okay, we remove the DC levels. We remove the zero mean, so that all data are start from zero. Okay, and then we estimate the data based on the impulse response. Okay, so after the data has been pre-processing, detrend, remove mean, okay, remove outliers. So we test using an impulse response and to see the correlation analysis. Okay, time constant and other things that are available for impulse. So you can see that it gives the response as shown here. Okay, so you can see that if we plot all the points, okay, all the 0 points, you can see that. Okay, clear first. Okay. So it goes out like this. Okay. So something like this, right? So that is the impulse response. Estimating is a second order system. Okay. So the command that we use to see the 99% confidence interval is impulse ZE SD3 field, okay, which is written in the slides. So you can see that the field is at the yellow zone here, okay, which is acceptable for a second order response of impulse. Then we propose the models. So in this slide, we propose two models for this hot dryer data. The first one is the M1, okay? M1 is the model one, which is using a parametric estimation prediction error method, okay, of the ZE data. So we get the state space model, which is written here, okay? So if you can see that this is a continuous state space model, X equal to AX plus BU plus KE. So this one is on the error part. Y is equal to CX plus DU plus E, error part. So A is the system matrix, B is the input matrix, C is the output matrix, D is the feed-forward matrix, and E is the stochastic part or the disturbance part. So you can see that when we use a prediction error method, so we get the system matrix is 3 by 3. Okay, so the proposed third order system, okay, for this particular data. And the matrix input is 3 by 1, which is the power, and the temperature of the output matrix is 1 by 3, which is the temperature. And matrix D is 0. The feed-forward matrix is 0. And matrix K, which is the noise, is 3 by 1, which is x1, x2, x3, and the initial condition is 0. So for model validation of the data, so we are using two methods, which is the loss function and the final prediction error. So you can see that the value of the loss functions and the FPE is almost 0. So if it's almost 0, the results, the model is accepted and can be used for further designs of the controller. And then this data will be tested on using a Bode, okay, Bode plot for the frequency response. So when we plot the Bode plot, you can see that the magnitude response is start from here, okay, it goes down like this, okay. So it proposed that this one is a second order system because the slope is minus 40 decibel per decade. And we also analyze using a Nyquist, which is another option for frequency response. Okay, so it give you the Nyquist plot. So this one you learn during your undergraduate, where this one is the real part, and this is the imaginary part. And we also test using a step response. So the step response shown here, where you have red one, which is the blue. Blue is for the estimated one, estimated model, and the red is the real, okay, the real data. So it almost follow the estimated step model. Is almost follow the real data, which is noted as red color. And so second order with delay, a little bit time delay here. If you look at this response, okay. So 0 is here, so there is a time delay a little bit here, okay, a very small one, okay, about 0.2 or 0.3 seconds. Okay, and then we propose a model, the second model, which is the parametric model. Okay, so parametric model is shown here with the two poles, 1, 0, and 3 delays. Okay, can be obtained using the ARX model, okay, as shown here. So the ARX, which is the ZE, the real data, 2, 2, 3, meaning that this system have two poles, 1, 0, and 3 delays. Okay, so the notation is here. So why 1, 0? Why not 1 is here? The calculation is 2 minus 1. So that's why the 0 become 1. Okay, but the coding is 2, 2, 3, meaning that two poles, 1, 0, and 3 delays, meaning that the equation will be something like this. There is 1, 0, and 1 s squared with the time delay. Okay, so there is 1 zeros and 2 poles at the bottom. Okay, so it's SM2. So we run using a MATLAB. So this is the equations for the ARX model. So the transfer function will be y over u, okay, is equal to b divided by a, okay. So the b will go to the numerator transfer functions, while the a will go to the denominator transfer functions. And the loss function is almost zero, and the FPE functions is almost zero. So how good an estimated model that we get? So we get M1 in state space model, then M2 using the parametric model, which is ARX 223. So one way to find out the model is good or not is to compare the model with the measured output. Okay, so we propose M1 model, we propose M2 model. Both are estimated, okay, or predicted. Then we compare with the real data, which is the measured output. Okay, so we select a portions, let's say 800 to 900. Then we validate the data as shown here. Okay, ZB, draw 800 to 900. Then we detrend and then we compare. So we can see that we compare M1 with the real data. M1 is the state space data. So the fit is 88.73%. Ideal is 100%, meaning that if ideal fit is 100%, M1 will be on the top of the measurement output curve. Okay, but this one is, you can see that there is a blue and black here. So the blue is the estimated M1, the black is the real data, measured data. So you can see there is outliers a little bit here, outliers a little bit here, outliers a little bit here, okay. So you can see that it didn't follow exactly. So when we calculate, the best fit is 88.73%. So the agreement considered very good, but can be further improved, because usually the theory said the best fit must be 90% above, okay? 90% above. So this one is 88.73, is about 89%, okay? So it can be further improved. It can be further improved in order to achieve this best fit above 90%. Then we compare with M2. M2 is the parametric model, ARX 223. Okay, so 223 will give you 88.43, which is labeled as red legend. So now we have three legend. One is black, which is the real data measurement. Blue is the state space model, estimated first state space model. And red is the estimated parametric model, ARX 223. Okay, so it's not much different. Both is 88% and 89%. So consider the agreement is very good and can be further improved. Then we try to get the value of the poles and zero. So in M1, the metric system is 3 by 3. So meaning that it has what do you mean that 3 poles, okay? Because the higher order is 3, but M2 the poles is only 2, okay? So PZMap is the function in MATLAB which give you the plotting of the mapping of the poles and zero, okay, in the S plane or in the Z plane. Okay, the location of the poles may be here, or zeros over here. Okay, or maybe it's on the top of imaginary axis. So this kind of mapping, we call it as a PZ map. Okay, so when we plot the poles and zero, M1 and M2 together, so you can see that we have for the blue one, so we have 3 poles, and the red one, so we have 2 poles and 1 0. So it's this very small. Okay, so we zoom it. Okay, we zoom. So you can see that much better here. Okay, there is the blue is the M1, the red is the M2 model. M stands for model. Okay, so when we zoom a little bit more, so you can see that the positions of the poles and zero. The red one is the ARX223. Okay, 2 poles and 1 0, while the blue one is the state space model. Okay, third order. So we have third poles 1, 2, and 3 over here. Okay, then we analyze using a Bode plot. Okay, for M1 and M2 together. So not much different because the best fit is about 88%, which is noted as the blue line and the green line. Okay, then put together with the real data. Okay, M1, M2, and GS estimation model. Then we compare with the Nyquist plot. It also give a good agreement, meaning that the shape is about the same, right? All right. So now, as I told you before, so I'm going to share with you how to use the MATLAB data, which is here. Where is the program? Here. Okay. Can you see the MATLAB?
Yes, Prof.
Yeah.
Yeah.
As I told you before, we need to load the data, load dryer 2. Okay. You can see there, load dryer 2. Just type at the command. Okay. So there is a, what do you call that, double prompt. So load dryer 2. Okay. So when you load the dryer 2, so you load the data, which is consists of the input and the output. Okay. So go back to the MATLAB. So you enter, and then you type U2. Okay. You type U2. There the data. So Y2. There is the data. So when you plot bracket U2, okay, you can see that that is the data for the input. Okay. Okay. Can you see the data or the input?
Yes, Doctor.
0 to 1000. Okay.
Yeah.
0 to 1000. That is the input. So now we are going to plot.
Is this random input, yeah?
Yeah, it's a random input, brother. Yeah. Plot PLOT, plot Y2. Okay. Okay. So it will become a plot y2. The plot will be shown here. Okay. So this is the output. Okay, if you follow my slide 5E, you type the command in the MATLAB, so you will get this kind of plot, right? So the output, this is the output. Previously was the input. So what I'm going to do now is to ask you to use the GUI, graphic user interface. Graphic user interface in order to plot the data. So you go back to the MATLAB here. Okay. So in order to use the GUI, so we type ident, I-D-E-N-T. Okay. You type ident. So if I can share with the okay. So just now is U2, then plot U2, okay. Then I ask you to Y2, enter, and then plot Y2, okay. So the next one is you have to, for in process for GUI, so we type IDENT, ident, okay. That is the short form to call the graphic user interface, okay. So where is it? Here. Okay, ident, enter. Okay, you can see that there is a, oops. Okay, can you see this box? Hello?
No, no, there's no blocks.
No box, okay, I have to share. Oh yeah, you have to share, right. Can you see the box?
Yes.
Okay, so now we are going to do some business, okay, import, export. Okay, so we're going to import the data that we already run in the MATLAB double prompt. So the data is in time domain, okay, data in time domain. So you also can import data in frequency domain or any data object or any examples. So we are going to import data from the input, which is U2. Okay, can you see U2? Hello?
No.
No? Okay. When you click the import data, so it will come like this, U2. Can you see U2?
Yes.
Okay. Then Y2. Okay. So input is U2 and output is Y2. And the data is dryer. Dryer. Okay. You can put your name as well. Alkali also can. You can put Saravanan also can. Okay. No problem. So starting time is 0. And then the sampling time is what?
0.08.
0.08. Okay. Then you have to label more. Can you see?
Yes.
Next window, which is the input is power. The heater power. The output is the
Temperature.
temperature. Okay. And then the unit for the power is watt. And the output is the
Degree Celsius.
Celsius. Celsius. Okay. All right. So then we import. Okay. So when we import, okay. So when we import, we'll go to here. Can you see the blue line?
Yes.
That is your data that you import. Can I see the plot? So you go to the bottom, you just time plot. So you can see the plotting of the can you see? Can you see?
Yes.
Okay. So the top one is the output. The bottom one is the input. Okay. So this is we call as the time domain data. Okay. The plot in the time domain. Right. And then if we want to see the other plotting, for example, spectra of the data. Okay, so we also can see the data spectra. Just click at the data spectra. So you can see that this is the data spectra, the temperature, and the power spectrum of the temperature. Okay. So temperature and power versus frequency. Or you can see you want to see the frequency functions. Also can, okay, which is the here, the Bode plot. So this is the frequency functions. Okay, so we are not using the power spectra. We are not using the frequency functions. So we just use the time plot. Okay, so so from the time plot, what is your observation? Alkaline. What is your observations?
Yes.
What is your observation, brother? The plotting?
My observation is that from 0 to, I can say, 40 seconds, the system power is stable.
Oh, okay, thank you.
But
Thank you for your observation. Actually, can be further improved. Hassin Abrar, what is your observations?
My observation is it is quite fluctuating.
Fluctuating. Okay.
the pattern is almost similar. No human eye, no significant difference actually.
Okay lah. Last chance, Tamani. Tamani, Ahi Tamani.
Prof, I cannot observe any difference actually. Everything looks the same.
Everything looks the same. So you are not critical enough. Okay, so if you look here, I use a red color. See, is it start from zero? Is it start from zero?
No.
Meaning that there is a DC offset in the data.
Yes.
There is a DC offset in the data, so we need to remove the DC offset. Okay. Okay, so I clear this one first. Okay, share. Okay, so we have to do the pre-process. Okay, so what is the pre-process? Pre-process is the action taken by us to clean up the data. Clean up the data from the unnecessary frequency, unnecessary DC offset, unnecessary outliers, okay? And then we have to remove the model's DC offset by using the remove means, okay? Remove means, DC levels. So we remove it, okay? So you can see, can you see the graph after we remove the means? I share with you. Okay, can you see?
Yes.
We have a blue line, we have a green line. The blue line is the before pre-processing. Okay, so the green line is after pre-processing. Okay.
Prof, we captured just 80 data.
For display 80 data, we cannot display 1000 because it will close, very close. So you cannot see the difference. So GUI will plot the first 100.
But if I want to adjust
for display purpose, actually the data will be remove means from number 1 data until 1000. But for purpose, for display purpose, it show the first 80. Okay.
Okay, I see.
80. Because if you show 1000, so it will be very close. So very close, so very hard to explain to the students.
Yes.
First time, okay. Right. So now you can see that the green data start from 0 input and the output, right? So we go back to the GUI. Okay. So now we have to do pre-process for. So we deactivate the blue line. Deactivate. So deactivate the bold loss. There is no bold. So when the line is bold, meaning it is active data. When there is no bold, meaning that the data is not active. Okay. So what we do is we drag this one to the working data. Okay. So it become dry ED data, the data that has been removed means. Okay. Then we go to the pre-processing, then we select the range. Okay, we select the range. Okay, so this is the data, the green data that is start from 0. Okay, start from 0, so we have to divide into 2. Why divide into 2? So that is the procedure. In the system ID procedure, so we have 1000 samples. The first 500 is for estimation. Okay, insert. Okay, so insert, and then go back to the so you can see here. Okay, so the first 500, the red one, for the estimation. Okay. Then we go to the pre-processing again, select range. So then the remaining 500, 501 until 1000 is for the validation. So dry V. Okay, insert. So now you can see 2 colors. Okay, this data actually is the green data. The green data meaning that the pre-processing data after we remove the means, the DC levels. And after we remove the DC levels, we divide the data into 2. The first 500 is for the estimation, the red color. and the remaining 500, which is this color. This color, we call it as the turquoise color. Is a mix blue and green, turquoise, okay? Is for the estimations.
Prof, we didn't see how to get this plot.
Yeah, I show you, yeah?
No, we didn't see because you didn't share the slide, the block.
Oh, this one, this slide.
Yeah. For this, how we can get this one?
Yeah, is in the chapter 5B. I will go into chapter 5B shortly. I show the demo first.
Okay.
All right. Right. Okay. Now, we already have two data, which is the estimation and the validation. So we deactivate this one, remove means. So the green ball is lost now, it's missing. And then we drag and drop the estimation red color. Okay. And the validation, go to the validation box here. Okay. So you can see here, E, estimation, V is for the validations. Okay. Now, after we divide the data, so we're going to estimate. Okay. So estimate using so many models here, transfer function models, state space model, process model, polynomial models, nonlinear model, spectral model, correlation model, refined existing model, and quick start. Quick start meaning the computer choose the model for you. Okay, so now we're going to choose a polynomial model. Okay, so we are going to choose the ARX model, which is we change to let's say we change to 2, 2, 3, two poles.
Prof, we can't see the block now. When you write something, we can see the block.
You can or you can't?
Can't. We can't.
Oh, you didn't see?
Yeah.
Okay, here, sorry.
No problem.
Here.
Yeah, okay.
Okay. ARX 223, meaning that 2 poles, 1 zeros, time delay 3. Okay, so we estimated. We choose the suitable model structure. Okay, and then the predictions here. Okay, predict. Then we estimate. Okay, using a ARX using a least square method. Okay, that we learn in chapter 4. So computer calculate for you. So there you go. Okay. Go to the So can you see here? ARX 223?
Yes.
Okay. So now we are going to compare the real, the estimated ARX 223 with the real data. So we click at the model output. Okay. So we click at the model output. So I share with you the model output, the comparison between the estimated model and the real model. Can you see?
Yes.
The black one is the real data, the black line. Okay, and the blue line is the estimated model, which is ARX 223, and 89.03 is the best fit percentage. So 89.03 is really near to 90%. Okay, so only 1% left to be 90%. So for me, it's okay. 89.03. Okay, it's okay. Okay, but can be further improved. Right. So what is the model? Okay, so what is the mathematical model? The mathematical model is here. Go to the MATLAB here. Share. The real, the mathematical model, the numerical one, you just click here, double click at that graph. It will give you one windows, okay, like this, okay? Can you see?
Yes.
Can you see that? So the discrete models, ARX models, is A polynomial, remember, chapter 3, and B polynomial, which is here. So Y over U, the transfer function of ARX model, is B divided by A. Okay, B divided by A, right? Then you can see that these models, which is known as ARX 223. Okay. So we go back to the here. Okay. Okay. So we already see the model output. We already see the transfer functions. Okay. Model output, you just click at the box here. Okay. If you click model output, it will give you the graph. If you want to see the details of the ARX 223, the B polynomials and the A polynomials, you just click at the ARX 223 box here. You just double click, okay? And if you want to see the model validation, model residuals, okay? So here, this is the correlations, okay, for model residuals, not important. The final prediction error is, I think, in the, if you double click here, it will give you the FPE and the AIC, the model validation, which is very, very small. Okay. Then you can go to the frequency response. It can show you the transient response and the poles and zero poles. So let's see the poles and zero poles. So 223, okay, 223 is the, this is the poles and zeros, 2 poles. Can you see? Can you see? Okay.
Yes.
So if you want to know the value, you just click at the zeros. Oops. Oh, dia jadi zoom pula. Okay. Never mind, it's okay. So if you want to find the zeros and poles value, you have to use the calculator in order to do that. So let's go to the slide 5B. So that is the introduction of it. So slide 5, go to here. Okay, I stop sharing here. I open, wait. Okay, close here, close here. No, okay, minimize. No, okay, minimize. So go to the 5B. So 5B is in this slide. Okay, everybody goes to 5B, please. Okay, so this is the slide 5B. So okay, so we are using the same data, but using a GUI, graphic user interface. So as I told you before, we are using ident function to bring out the GUI interface, graphic user interface. Then we call the data dryer to with 1,000 data samples for input and for the output, as represented by U2 and Y2. So this is the schematic diagram for the process, okay, the real process, and the process works, okay, as I told you before in chapter 5A. Okay, so we call IDEN, so we go the system ID toolbox like this, okay, so where you have to import the data. So you import the data, okay, there's the data, U2 and Y2, okay, you insert U2 and Y2 with the sampling intervals 80 milliseconds, so 0.08 second. So when the question asks you what is the sampling frequency, so sampling frequency is 1 over 0.08 second, so which is 12.5 Hertz. So insert the 0.08 and then call the name of data is dry, or whatever name you want to put. Put the unit, the input is power in watt, the output is temperature in degrees Celsius. Okay, for bookkeeping lah. Then you import. So when you import, you will get the dry icon here, the blue dry data, which is a raw data. Raw data meaning before pre-process. Then you check the time plot. So there, the time plot here, okay, the output and the input. Then I ask you the observations. So mostly some said fluctuate, stable, okay. Actually they don't know what they comment, okay. So the comment is, the observation is the data is not start from zero, okay. So there is a DC levels in that data. We need to remove it, okay. We need to remove it via pre-process by remove means, okay. Remove means in the pre-processed data. So when we remove means, so the blue line will become green line, which is start from zero for both input and output. Okay, and then we put some, what do you call that, the icon will come out for the remove mean data. So meaning that the blue data now is not used anymore, because we are using the update data after pre-processing, which is the green data, the green line, okay. And then we select range. Select range is we divide the 1,000 data into two. The first 5,000, the first 500 for estimation. The remaining 500 is for validation, okay. So it becomes like this, okay. Right, the first 500 and the remaining 500. Then we insert. So there is a red and red data and green data, okay, after we divide it. Then you put insert data at the working data. Working data is the estimated data, the first 500. Drag and drop, okay, you drag and drop to the working data, the first 500, then you drag and drop the remaining 500 data at the validation, okay, estimation, validation. Estimation, you estimate the model. Validation is you estimate the error, the final prediction error, the best fit and so on, okay. So that is considered as on the validation part, okay. So it become like this. So we have an estimation on the red color and the validation on the turquoise color. Right, and then we estimate the data, the model structure, okay. So the model structure here is impulse, okay. So it will give you something like this, impulse models. Okay, and then spectrum models, because we are using a quick start. So the computer will choose for you. Okay, so that is the frequency response. And then if you use a parametric model, so we have a ARX model, which is we can use the combination 441, for example, meaning that we have 4 poles, 3 zeros, and time delay equal to 1. 441. Okay. So when we run 441, okay, so we will get the mathematical model A and B polynomials. Okay, A at 4th order, okay, and B at 3rd order. Okay, so the model output is shown here. But the best fit for ARX 441 is 89.02. 89.02. Here, 89%. Okay, you can see the black and the red line. The black is the real data. The red line is the estimated data. And then we choose a 223. Just now, we choose a 223, 2 poles, 1 zeros, and time delay 3. Okay, so we estimate. So we get these transfer functions, which is A polynomials, highest order is 2, B polynomial, highest order is 1. Then see the plot, 89.18, 89%, okay, for ARX 223, more or less the same, okay. Then the transient and frequency response also show about the same, which is a second order system. Then we make discussions, okay, for 3 models, which is 441, 331, and 223. Okay, 441 is 4 poles, 4th order. 331 is 3rd order. 223 is a 2nd order. So analyze with the detailed analysis. Okay, this is a 441. Black line is the real data, blue line is the simulated data estimations. Okay, and the data is shown here. Okay, you can see that below the A and B polynomial, there is a loss function 0, FPE, final prediction error also 0. This is the model validation, which is almost close to 0, so the model is accepted. Then we zoom it, you can see that the A polynomials, 4th order, and B polynomials, 3rd order, because you can factorize this, okay, it becomes 0. Okay, the loss function is almost 0, FPE is almost 0. So the ARX 441 model is here. Okay, you can see that the model, okay, 4th order and 3rd order, because this one can be factorized. Okay, when you equal to 0, it can be factorized and become 0. Okay, so how are we going to find the poles and the zeros value? So the way we do that is here, after we simplify, okay, this is what I told you before, the models just now, okay, this one can be factorized, okay, can be factorized. So it left 3rd order here and 4th order below. Okay, this one you use your calculator. Okay, use your calculator. 1, 2.4, 49.6, and 42.3. Okay, so you enter to your calculator. So you will get the zeros roots. Okay, the zeros roots as minus 0.766 plus minus J 6.9, and Z3 is minus 0.87 for the 0. For the poles, you key in this one, is the 4th order, 1, minus 1.125, 0.0, 0.2, and 0.05. You cannot use old calculator. You have to use this new calculator, white color. Okay, this one can factorize the roots until fourth order. Okay, the new calculator. Okay, can you see, brother? You see fish or you see calculator? Can you see the calculator?
We can see it. We can see screen.
Can see the
We cannot see.
Can see? Is a white color. So this new calculator by Casio can calculate 4 roots, okay, which is P1, P2, P3, and P4. Okay. In case you have a case of fourth order system. So when you plot the 441 in the Z plane, so it will give you 4 poles and 3 zeros. So in this case, the zeros is here, is here, is here, 3. Poles is here, 2, and here 3. And this line, we call it as a unit circle. Okay, everybody said unit circle. Hello? Unit circle.
Unit circle.
Yes, thank you very much. So this is Z plane. Z plane, it's not S plane, Z plane. Z plane is the only plane which have a unit circle. S plane, no unit circles. Okay, for this is for discrete transfer function. Understand?
Yes.
All right, thank you. Then we go to the rest of the analysis, which the correlation, autocorrelations, okay, which is shown here. The step response show some time delay here. The frequency response show behavior like a second order system, and the cross correlation and autocorrelations of the input and output as shown in the graph. Then we go to the 331. 331 is 3 poles, 2 0, and 1 time delay. Okay, so it gives you as the black line, real measurement, green line, simulation or estimation. Okay, so we run the 331, this is not 441, the 331 model is shown here. So we zoom it. Okay, so we get the A polynomial, which is a third order, and B polynomial, which is a second order. Okay, and the transfer function is shown here. Then we do some analysis. Okay, you can see that this one can be factorized. Okay, so we factorize, it become like this. Okay, so when you equal to 0, all this, so we will get 2 zeros, which is here, minus 0.4 plus minus J6. And if you factorize this equal to 0, you will get 3 poles, which is 0.7, 0.44 plus minus J 0.07, right? So we plot it. Then you will get 2 zeros, okay, and 3 poles inside unit circles, okay. So usually if zeros is outside unit circle, we call it as the non-minimum phase system, okay, non-minimum phase system. System stable. Okay, system stable because all poles inside unit circle. If there is poles outside unit circle, okay, let's say there is a pole here, okay, brother, is outside unit circle, meaning that the system is unstable, okay. So the analysis of others, non-parametric method, which is correlation, frequency, and time response. Then 223, which is 89.18. Okay. Here is the model, mathematical model. Okay. And I think this is the best, okay, because as I told you before, the closed loop of the process trainer is second order system. Okay. So this is the best model that we can represent. Okay. Which is have one zeros. Okay. This one, if you equal to 0, so this one will cancel out. Okay, it will cancel out. So only 1 zeros and 2 poles, right? And you can see that the poles is inside unit circle. Okay, meaning that the system is stable. And the zeros also inside the unit circle. So the system is stable and minimum phase 223. So we compare all together 441, 223, and 331. The three parametrics model, ARX model, but different combination of poles and zeros. Okay, it gives about 89 to 88%, which is good. So after the class, after the test, before you sleep, you use this Y2 and U2 data, try to get above 90%. Okay? Then you WhatsApp direct to me if you get more than 90%. Can you do that? Hello?
Yes, Prof, but how can I improve the
90%, best fit 90%. The one that I get here is 89.61, 89.18, 88.86. So can you find the good model structure that can give you 90%?
Okay.
Okay?
Okay.
So this is the comparisons. Okay? So if you have no idea what model structure you want to use, at the estimation method, you just choose quick start. Quick start meaning the computer will choose for you. Okay, idea lah, which is the best model structure that you can use. Okay, if anybody get 90%, please WhatsApp me. Okay, now we have a break. Okay, for 5 minutes break. Preparation for the test. Okay, so please, brothers, on your video. Okay, because we're going to do test 2. Okay, I will release the password.
Prof, can you extend the time so that we break time, so that we fill the plagiarism form and the cover page?
I already messaged to you.
Yes, we can fill it. 5 minutes is not enough.
Oh, not
maybe
enough. Okay, you want 10 minutes. Okay, 10 minutes.
Maybe.
3:35. Okay, 3:35. Everybody on the video, please. Can you access to the e-learning? Can you access to the e-learning? Can you access e-learning?
Yes.
Can you download the question? Can you download the question?
Yes.
Yeah. Can you open the question?
No.
Anybody who can open the question? No?
No.
Okay.
Asking password.
Why you can open the question?
They have password.
Password, So you need a password,
Yeah.
Can you fill up the green cover? The green cover.
Yeah. Yes, sir.
Can we fill up the plagiarism form?
Yes.
Okay. Are you ready? All ready? So I give you about 5 minutes, okay? Okay, is it okay? 5 minutes.
Okay, Prof.
3:35, we start. Okay, attendance. Attendance. Ahmad Ahsan.
Ya, Prof.
Angkat tangan, angkat tangan. Okay. Hasin Abrar. Raise your hand. Oh, Hasin. From Bangladesh. Huh? G. Bangladesh. Muktaba Hasan. Muktaba Hasan.
Yes.
Okay. Sudan. Arab Saudi.
Yes.
Muhammad Al-Kalain. Al-Kali. Muhammad Al-Kali.
Yes, Prof.
Video on, please.
Okay.
Okay. Okay. What time, Nigeria? What time?
Now, to 9. 25 minutes to 9. 8:36 now.
Okay, okay, okay.
8:36.
Muhammad Syafiq. Angkat tangan. Syafiq. Okay. Saravanan Kumar. Okay. Tamani Piri.
Present.
Tamani from
Zambia.
Zambia.
Zambia. Zauji.
Yes, Prof.
Ni hao.
你好。
N hao. Abu Nasir. Abu Nasir. Abu Nasir. Abu Nasir Hassan Mahmud. Okay, everybody in. Right. So the password is password is PW PW 6121 PW 6121. Can you open? PW 6121.
Yes, sir.
Okay? Okay,
Yeah, okay.
start now. Can start now. One hour, 15 minutes. 1 hour, 15 minutes. Okay?
Prof. Prof. Prof.
Yes. Yeah. Kali.
Yes. To how many decimal places we can make our estimate?
2.
4 decimal.
Yeah, 2 decimal. 2.
2. Okay.
Excuse me, Prof. Prof.
Yes.
There's only one question.
Only one question. You have A and B. Answer all questions.
Okay, thank you.
Those who are finished can submit online via e-learning. Make sure you scan the green cover, plagiarism form, your answer script together in one PDF file. Okay. Only one file submit. The file consists of green cover, plagiarism form, and your answer script.
Doctor, doctor,
Yep.
doctor, for the to calculate the mean square error,
Yeah.
we have to use the A we get from the generalized least square method, right? I mean, the second procedure, right?
Yeah. Mean square error is the actual is a modulus
Yeah.
of actual value minus predicted value.
Yeah.
Okay.
Okay.
Modulus and plus the next value plus the next value divided by 3.
Okay. So we that one we used for the generalized least square, right? For the B, right?
You
Question B.
calculate the mean square error for the prediction value.
Prediction value by
y cap, y cap 2, y cap 3, y cap 4.
okay.
Yes.
Yeah.
Apik.
Now about the last.
Apik. Tak dengar.
For calculate MS.
Tak dengar, Apik.
Okay, I will WhatsApp. I will WhatsApp.
Tak dengar. Chat. Tulis chat. Times remaining 1 minute. Times remaining 1 minute. Okay, please stop writing. Okay, please stop writing and send your answer script, your cover, your plagiarism form, one file PDF through e-learning now. There is a time limit for submissions, so please be faster. Stop writing. Scan your answer, and then I will wait at the e-learning. So I will end the video because you want to use it for scanning for PDF, okay?
I got submitted, so.
I
got submitted.
Dah hantar?
Dah hantar.
Okay. So saya end the video, eh?
Okay.